I want to focus on having finished up the circuit, at least for power production. It's still not regulated. It goes to infinite oblivion if you keep running it, and very fast too. It's pretty explosive. So I found a way to possibly slow it down, but I'm having problems implementing it. But in the meantime, I thought I'd mention a few things and go over some of the screenshots. So here's the node voltages of this simple analog computer, which has no switches. It's just an input and an accumulation and a drainage through the out, and a load drained through the very input line that inputs it also serves as the output, because there is so much accumulation of voltage that coming in, accumulating on the inside, accumulation of reactive power that most of which converts into real power, because everything gets aligned automatically. Oh no, go away. The current and the voltage get in alignment, but then something silly happens that I want to get to. But I'm prefacing first by starting up with this warm-up material. Okay, so these are the node voltages, and notice how high they are. So here there's gigavolts, here there's megavolts, with reference to ground, which is where the input is located over to the right off screen here. So I just wanted to get you familiarized with how this thing builds up. Now let's move on to the next slide. If I can go in the right direction. Nope, that was the wrong direction. Okay, that's the circuit from a faraway view. So we have two core modules that are true LMD analog computer modules, and then two buffer modules, bookend modules on either side, that don't really qualify the same way, because they're not united to another module, and so they're a bookend, although they are patterned off of the same core, except for there's no transformer on the end here. It's just a plain inductor, and there's also a parallel capacitor here. But otherwise it's the same. Now, what's interesting I found is there's certain requirements to make the circuit work. One of which is that the input frequency has to be 300 gigahertz minimum. But if you go too high, it seems to be a resonance, a sweet spot. So if you raise that frequency, if you raise that frequency too high, you go out of the sweet spot, and then you don't get this over unity, which I'm going to describe shortly, the nature of this over unity. Let's see. So that's one requirement, is that a certain range, and the minimum of which is 300 gigahertz. And it goes up a little bit, but you're allowed a little wiggle room, 400, 500, but you can't go too far. The other requirement is that the voltage input is really a stimulus. It's not an energy source. So we're not getting energy from the air or whatever. It's just a stimulating sine wave of a very high frequency. Has to be in the range of about a microvolt minimum and 10 volts maximum, more or less, give or take. I'm just extrapolating to whole powers of 10. Anything greater than that or less than that doesn't work. So these are windows of opportunity, parameters of minimums and maximums you have to stay within. And within those parameters, you get a lot of wiggle room. You can do whatever you like. Now, the capacitors in this thing, not the parallel capacitors in the bookend, those are 2 microfarads, but all the other capacitors in these LMD modules are 10 microfarads. And less doesn't work, and I would imagine more doesn't work, but I didn't try because I'm trying to scale this thing down. What's the minimum size I have to make this in order for it to take off? And so a minimum frequency is 300 gigahertz, minimum size on the analog module, LMD module capacitances is 10 microfarads, and I'm assuming 100 milliohms of equivalent series resistance within each of these capacitors. Okay? Now, the transformers linking these modules together are 1 millihenry on both the left and right coil. And it doesn't matter what the mutual coupling, the magnetic coupling, the coupling coefficient happens to be. You can make it as high as you like, you can make it as low as you like. There seems to be a sweet spot at around 60% coupling coefficient and downwards, and to, I don't know, something like 0.001 or something. It's really bizarre. Remove the transformers and the whole thing goes dead. But so long as you have the magnetic coupling there between the two coils of what constitutes, functionally speaking, a transformer, it doesn't seem to matter how much coupling coefficient you have between the coils. In fact, it gets pretty good when you reduce it down to an amount of coupling similar to that of a motor between the rotor and the stator, you know, with an air gap between them. Very interesting. Now, the two end coils on the two bookend modules are very small. I think they're 1 microhenry, just like the capacitor next to them is 2 microfarads. And when I make my coils, I can't do it on the transformers because the microcap won't let me. But on these two end coils and any other coils, such as the load coil over here, the inductive load, I always try to put an equivalent series resistance, and I assume a 25 gauge wire, 25 AWG, which basically for every henry of inductance from that gauge wire, I can approximate, or I can, you know, guess estimate that it's going to be 1 ohm of resistance for the length of wire that constitutes 1 henry of inductance. So I give it, you know, its equivalent series resistance because I want to make sure my coils have resistance to make them realistic. I can't do that on the transformers, and that may be a problem in that it may not be realistic. These may be idealistic transformers that don't have equivalent series resistance in them. In fact, I think they are, now that I think of it. So I'm going to have to check on that, because microcap does give you alternative transformers. They give you a few options, not too many. Now, I just picked the first one I saw, and everything's been working fine, but it's always been in the back of my mind, well, maybe this isn't realistic, because they never allow me to put in equivalent series resistance. Maybe they have a default amount that's already built in. I don't know. And that's important. Now, another requirement of the circuit is that I short out both sides of each of these three linking transformers with a capacitor that shorts them out. And wouldn't you know it, I make the capacitors the same as all the other capacitors, 10 microfarads. It's very interesting that it requires that. Now, we also need, in order to shrink this down and not have it be, you know, lots of farads on the capacitors required and lots of inductance on the coils of transformers. In order to shrink this down, I have to add in negative resistance to enhance the circuit. It's not a requirement. It just enhances it so that I'm able to then shrink it down so the circuit doesn't take up the size of a warehouse or something similar. So I put in parallel negative resistance in the form of a spark gap when it breaks down its voltage breakdown threshold, in parallel with only the topmost capacitors on each of these 4 modules. I don't do it on the bottom because I don't have to, but minimally, so I'm trying to minimize here. As a minimalist, I do have to put it in parallel with at least one side. If we draw a mirror of symmetry axis horizontally down the midriff of all 4 modules, and so that we can flip the bottom onto the top and the top onto the bottom. It's the top side that I chose to give it, which might be a requirement that it's on the same side that gets stimulated. I don't know. Let's see what else is required in here. Okay, that's a discussion of the circuit. Now I want to move on to the, if I go in the right direction. Now, this is a depiction of the virtual oscilloscope tracing of, what is it? It's the radio tuner. Now the radio tuner, I changed the sine wave generator to not be a sine wave generator because basically a sine wave generator puts out, if it's a digital one, puts out 3 volts and you feed it 9 to 12, but 12 is better for a nice clean sine wave. And since I don't have switches anymore to drain off the load or on some other link, on some other pathway other than my input, and I don't have a switch here to cut off the input to protect it from all the backwash of energy that wants to go back into there. Suffice to say, it cannot be a sine wave generator anymore. So now I call it a radio tuner. And now I don't have to worry about just specifying that the radio tuner put out 1 microvolt, because a crystal radio set from the 1920s, if you analyze how much power does it pick up from its whip antenna, which is a piece of wire 1 meter long, is about on the order of 1 microvolt of input power, which is perfect. It just happens to be the amount I want to use. So we're not getting energy from the air. I have to repeat this a few times. We're getting stimulus from the air, a nice sine wave of 1 microvolt of a high frequency, and that's it. Everything else is the recycling of reactive power, much of which converts over into real power. So most of it, just about all of it, in this particular instance, because when you analyze this thing early on, very often you'll find triangle waves. I don't have a screenshot of that, sorry to say. I did it on earlier versions of this to satisfy myself that I was creating triangle waves, and the current and the voltage were lockstep, 0 degrees phase relation between them. Thus I knew it was capacitive reactance that's driving this circuit, not inductive. That's why it's so explosive, and that's why I get triangle waves with 0 phase difference between the current and the voltage portions of the wave. Now here we're looking at the current of the radio tuner. So once it's been running for 300 picoseconds, and I'm getting ahead of myself, but there's a transition in here we'll focus on later. But the rest of this area after, it looks like 70, maybe 70 picoseconds, is very erratic. Now it's trying to grow, it's trying to have a high frequency here and grow, but then it breaks down into an erratic movement. And I'm going to get to in a minute the nature of this erratic movement, but I want you to see what the waveform looks like and then what the RMS average is. The RMS average looks like it's on the order of somewhere less than 400 amps coming out from the circuit. Coming out from the circuit and backwashing back into the radio tuner. Once the energy is built up here sufficiently enough to overpower the teensy little microvolt that's coming from the radio, that's continuing to come from the radio tuner because we didn't shut it off. So it's still coming in there, but it's overwhelmed by all this other energy that's coming back washing into it. Now this is the voltage sine wave that the radio tuner is still putting out after 300 picoseconds. So nothing is messed with the voltage coming out, coming out of the radio tuner. It's still a sine wave, and it's still at 300 gigahertz, and it's still 1 microvolt plus or minus. Hasn't changed. So that's why I have a tendency of looking at the current, because that tends to be the portion of this system that tends to change. Now here's the wattage input at the radio tuner. When you combine that microvolt sine wave with the amperage, this amperage, you get this RMS, which is 245 microwatts of input at the end, at the terminus, or at the time duration point of 300 picoseconds. So it's still rising, but far in deference to what the rest of the system is experiencing, which I'm going to show you in a second. Now here are the various amperage loads. The 1000 ohm resistor, the 10 farad capacitor, and the 1 Henry inductor, which is located, if I can go in the right direction here, which is located off to the side here. So we have the radio tuner at the top here. That's the first, well, there's a little capacitor of 10 picofarads separating the radio tuner from ground, which could be an aerial for all I know. But then we have the inductive load, and in parallel we have a capacitive load, and then below it we have the resistive load. And the resistive load helps to keep, I put it here for a reason, to help, because this has the greatest resistance of these items, it helps to keep all the voltage in the circuit and not leak out too readily, because I really don't want the voltage to come out. I want it to stay in here and build up. Okay? So we're moving right along here. So that's the 245 microwatts input at the radio tuner, and then these, so the green, let's see if I can do this. The green is the inductive load. That's the least. So here's the baseline up here. Here's the baseline up here. So the green is the inductive load. That's the least amount of amperage, okay? The red is the capacitive load, which is slightly less than the resistive load. The resistive load has the greatest amount of amperage. I won't try to analyze that. Why? I'll just move right along. Just describe it. Now here's the resistive voltage, the voltage of the resistive load. Here's the erratic waveform. Here you'll notice, I should keep repeating myself, whoops. Here you'll notice an exponential curve into the negative, and then it becomes erratic. And so I'm going to get to this in a minute. See, there's this exponential curve. All of these have exponential curvatures, and then it breaks up into erratic behavior. Here again, we have an exponential curve coming downward, and then it breaks up into erratic behavior. I'm repeating myself for a reason, because that's the whole point of this video, is to focus on that particular feature, even though I'm covering all this other stuff. So this is the voltage of the resistive load. Now here's the voltage of the inductive load. So we get a, I should back off here. We get a RMS of around 80 volts on the inductive load, 1 Henry inductor, and at the end of 300 picoseconds. And here we get the exponential rise downward into the negative, and then it breaks up into erratic behavior. Now here's the voltage of the capacitor. The capacitor RMS is at, it looks like 20 volts at the end of 300 picoseconds. So the amperages of these things are much higher than the voltage, and I think that has to do with the solder joints being 10 times less than 1 ohm. In other words, 100 milliohms tends to cause the amperage very often, more often than not, to be 10 times greater than the voltage at the loads, at the various loads. So here we have an exponential rise downward into the negative direction, and then it breaks up. And here's 3.8 thousand watts of RMS power on the 10 farad capacitor at the end of 300 picoseconds. And here's 4,000 watts of active power, not real power, not reactive power, at the 1 Henry inductive load. So even though the recycling of reactive power is what runs this, what escalates this phenomenon, but the end product is that this circuit manages to correct for power factor and put all the current and the voltage wave components of the wave back together again with 0 phase difference between them. It's really a remarkable, simple little circuit. Now, we get to the reason for the video. So here's a screenshot of the first 10 picoseconds of the circuit. And you'll notice there's a little triangular wave going on here, because that's the nature of the circuit, is capacitive reactance, which tends to be triangular. But then the radio tuner overwhelms that initial reactance and pipes up, and because it's starting to anyway, but finally it takes over and gives you a nice sine wave. And the only reason why it doesn't look smooth is because the simulator doesn't choose a lot of data points to make a nice smooth wave, but it looks pretty close and pretty approximate to what is happening, and so we get the idea, oh yeah, it's a sine wave happening here. But this is at 10 picoseconds in the very beginning. This is the current portion of the radio tuner. So we're not looking at the voltage, because the voltage is stable. It's the current that changes and shows how this circuit functions, how it behaves. So now we move on to 35 picoseconds, and now we get the nice sine wave. First the little squiggly triangle, and then the nice sine wave, and then now the sine wave is being pushed down exponentially in the negative direction at around 30 picoseconds, I would say. No, actually prior to that, around 25 picoseconds. Now the clean sine wave input is beginning to exponentially surge in a negative direction. And now that hyperbolic curvature, which we see here, breaks up into this erratic behavior over here. This is up to, looks like 120 picoseconds. Yeah. So the hyperbolic curvature of an exponential surge of input current is broken up into randomized disturbances of what we would like to think is chaotic output, or I should say buildup, within the circuit, backwashing back into the inputs. Sorry. Now, what is this chaos? What is the nature of the chaos? I am going to tell you. It is the flame, the electrical flame coming off the top end of a Tesla coil. That's what we're looking at. See, this is the nature of reactance, is to do its own thing when it wants to do it, how strongly it wants to do it, and not take orders from anyone. It's not very useful for our appliances, particularly for our electric motors. But boy, that's the way electrical reactance wants to behave. It's a flame. It's fire. We're toying with fire when we're toying with electrical reactance. And to some degree, we're doing so when we toy with electricity in general, but not really. Electricity, the way we like to deal with it, is rows and columns of trees or plants of corn, let's say. You're planting corn in a field, and you make row after row, and each row is a straight row of corn plant after corn plant after corn plant, all lined up in a nice, neat and tidy row that you can till the field, take your tiller through there and till the soil in between the rows of corn and walk in between the rows of corn. But that's not the way electrical reactance wants to behave. It wants to behave like a forest of trees who have seeded themselves naturally such that the trees are sporadically spread out all over the place in a very randomized fashion, what seems to be a randomized fashion, just like the leaves of, let's say, a conifer or any kind of tree seems to be randomized, but what we really call mathematically, it's a fractal. It appears to be a randomized condition, like no two snowflakes are alike, but in actuality, it's a growth form in which it has the choice on how to spread itself to dissipate its load. When a frond of a pine branch spreads out its fingers of leaves from a branch, it chooses its choice. It has total control over choosing what really doesn't matter specifically with each frond poking outward. What matters is the overall spread. Does it do its job in dissipating energy from out of the tree? Because the tree is acting as an antenna. It's an aerial, a grounded aerial, and it's sending out radio waves, but it's also picking up radio waves that the environment creates. All the living forms create radio waves, and they also pick them up. And trees are beautiful aerials at picking up. If you just connect your AM radio antenna lead to a tree by hammering an iron wire into the tree to reach the sap, you'll get very good reception. You'll damp down all your static background interference, and you'll strengthen the signal from the radio station, and it's awesome. And the tree doesn't have to have leaves on it. It just has to be a living tree. It's awesome what trees can do. Now remember, they are grounded, and the aerial at the radio station is sending out half of its energy through the air from the aerial, but half of it's sending through the ground, because that aerial is grounded at the radio station. And a tree picks up both and enhances it and boosts it and clarifies it and filters it. Now that's a life form, and that's what electrical reactance is. It's life. It's not orderly specifically, it's kind of randomized specifically, but in general, across the broad view, it's very well orchestrated to get the job done regardless of how randomized it might appear in every tiny little flame occurrence that seems random to us, but overall is totally doing its job of what it's supposed to do. Distribute energy and make sure it doesn't get bunched up all in one place. And that's growth. That's movement. The movement of a tree, the only kind of movement a plant can have, is not like an animal or an insect on wings or feet can move around. The only way a plant can move is to grow. And it grows, just like Eric Dollard showed us when he burnt the flame coming off of his Tesla coil, which is not exactly the same as the popular Tesla coils, but his Tesla coil, which has more capacitance than a normal Tesla coil, conventional Tesla coil, because Tesla made them that way. He didn't make them the way everybody makes them now, in which it's purely inductive, and then you have maybe capacitive relationship between the coils. No, he had capacitance between each turn of the coil, and that raised the capacitance of the coil such that he was able to make use of electrical capacitive reactance in order to build this flame phenomenon, this surging phenomenon of a bonfire, a roaring bonfire of surging electricity, seemingly coming out of nowhere or disappearing, as Eric Dollard has demonstrated recently, or disappearing. And that's the beauty of electrical reactance, particularly capacitive electrical reactance, is in that it has so much leverage. It has so much leverage that a little bit of work can produce a lot of results if you pay attention to your details. And that's why I stick to capacitive electrical reactance, because if you pay attention to the details, the net result is humongous. You will not be dissatisfied, but you have to pay attention to certain details. And it's only a handful, it's not a lot. And there's room for wiggling around. You don't have to be totally precise, and that's the beauty of the analog computer LMD module, is it allows you a little wiggle room. You don't have to be exactly everything precise, like my reactive motor at is.gd/reactive motor. Everything there had to be so precise, it was impossible to conceive of building it. But this, there's room for wiggling, and so you don't have to worry too much, so long as you know what your parameter limits, your minimums and maximums are. Now, if these transformers have no internal series resistance, does it matter? I bet you it doesn't. Remember, I reduced the coupling coefficient below 7. I've tried going as low as 0.001. So long as you don't remove these things, it's okay. It can have the weakest coupling coefficient on the planet. Now, what is resistance in a coil? That's going to impact the mutual inductance. It's going to delay it. So, in a sense, I've already done that. So I almost don't have to care about going and looking for a different transformer component in microcap, because I've already done an analogous experiment to see what would happen if the mutual inductance between the coils got vastly reduced. It doesn't matter so long as you short a capacitor between the two coils. So, in a sense, I'm finished. It's just, I don't know how to regulate this thing with a fast-acting switch. I'm not, obviously it's going to have to work with something. I'm trying different, I tried yesterday, again, there's no way around it. You got to bring switches in here, but what I had before was not entirely doing the total job I need to do. And so what I'm finding is I don't need any switches to basically build this thing, to make it run. I just need a switch to regulate the output. Now, I used to say that if you reduce the mutual inductance, you'd control this thing. But that was an LT Spice, and I may not have had these shorting capacitors underneath the transformer. And in LT Spice, I couldn't control it at all. It just blew up in my face. So this at least surges. It takes time to get to infinity. It doesn't just get there right away. In other words, the surge is not that fast, although it is semi-fast. And I'm looking at ways to slow it down without killing it at the same time. And that's the touchy part, because I don't want to kill it. I just want to slow it down, ease it up. And I thought that a duty cycle of putting batteries here, I got to back away. Putting a dead battery here, here, and here, and then switching them in and out with a certain duty cycle and a certain frequency of switching them in and out. I found, first of all, it kills the surge, but only so long as the battery is connected. Once the battery is disconnected, the surge returns because the energy is already stored in the system at a certain minimum, and the tendency of the circuit is to want to explode. That's the nature of the circuit. So by using a dead battery as a voltage regulator, I was hoping to switch them in and out to try to pace the growth, the exponential explosive growth of this thing, so that it doesn't happen so fast, and fake a circuit that is somewhat tolerable for our appliances to put up with it. Because right now, no appliance would put up with this power supply. Well, no way, I don't want to deal with this. You're going to blow me up. So that's what I'm thinking of doing at the moment. Because a flat DC source of voltage kills the oscillations that are going on in here, especially if you put it in the right place. So opposite the short, the capacitive short between the two sides of the transformer, on the other side of the circuit, the side that has the negative resistance, you put the battery to kill the negative resistance or kill the oscillations. I'm not quite sure what it's doing up there, but it seems to do the job. And I chose a voltage on the presumption that maybe a dead battery might be 1 femtovolt. That's 1 e to the negative 15. Obviously that's very dead. Dead batteries are not that low in voltage, but I chose it because, I don't know, I just picked a number. I don't know if that's realistic or not, but any voltage would kill it. Any DC voltage would kill this thing if you put the battery in the wrong place, or if you put the battery in the right place to do that. I just chose a dead battery because I'm hoping the dead battery won't explode, provided it does not become revived and take on a charge. Then it'll explode in the presence of the circuit. There's no question about that. So live, healthy batteries have no place in this circuit unless you want to explode them. Now, if I take an example from Richard Hackenberger in the EV motor, he ionized air. He created a capacitor of floating plates and put air through them. So, an alternative to a dead battery, which might be safer, is to put 2 plates, and then as your dielectric, compressed air or forced air to go in between the plates to ionize the air and carry the charge out. But that won't work. No, you know what would work is a diode. You know, that might be why microcap throws up matrix's singular error if I put diodes into this circuit, anywhere in this circuit. But the problem is a diode is very forceful, and a battery is a passive thing, and you pretty much act upon it. I mean, a dead battery is a passive thing. You act upon it. That's why I chose it, because it seems to be safer. Nothing blows up. I don't get any error. You know, I don't get any error messages blowing up in my face, because that's a different type of explosion. It's just a question of whether or not I can switch it in correctly. Now, I did get an error message, though. No, now that I remember, I did get a matrix's singular error message when I tried using... I took a, what do they call it? Switched capacitor macro, and I swapped out the capacitor and put in a dead battery, hoping that would work. But that is switched with resistors of different values. And it either killed the circuit, or I got a matrix's singular error, which tells me that the thing exploded in my face. So maybe dead batteries are not the right way to go. We got to do something in these 3 gaps to kill the circuit in a periodic fashion to regulate this thing. I'm just wondering what should be put in these gaps. Should it be a capacitor and blow air as our moving dielectric between the 2 plates of the capacitor? Then we could regulate the flow of air to well, first I should put in a capacitor here and see what happens. So we already have a capacitor here, a regular capacitor, but if we put another one here, let's see, air would be a very weak dielectric. So I would have to make a capacitor very low farads to start with. And moving air would be even less. It would be so low that it would not even be able to hold a charge. That's right. So how low can I take the capacitance of a capacitor placed in each of these 3 places to kill this circuit? But would it work? Because a battery works because it's polarized. So does it have to be an electrolytic capacitor? Well, how do you make an electrolytic capacitor? You have to put a battery. A diode. So maybe I should put in 1 diode alongside 1 capacitor and then vary the capacitance of the capacitor to see if I get any error messages and to see whether or not I kill the circuit. Because then if I do, then that would replace my need for using a dead battery. because a dead battery, I run the risk of the darn thing reviving and exploding in my face. So I really don't like the idea of dead batteries. David Bowling, I think that's, yeah, his name, on Energetic Forum. He says, you know, batteries have a tendency of reviving when you put them into a so-called radiant energy charger, which is, I don't like to use the word radiant because it's not an electrical engineering term. I like to be conventional. So it's a reactive power charger for batteries. And batteries are great at dealing with reactive power. This is what Ossie Callanan, discovered. So he used batteries as a means of converting reactive power into real power. Well, he didn't call it that. He said he was converting radiant energy into real energy. Be that as it may, regardless of how we confuse ourselves with different nomenclature, the fact of the matter remains, batteries might be useful provided they don't revive and then get recharged. So I'm going to try to steer away from that and instead move in the direction of a diode and a capacitor with a variable capacitance such that it's very low versus moderately low. You know, 10 microhenries is the minimum, actually, now that I think of it. So if I put a capacitor in here, even without a diode, of less farads than 10 microfarads, I may kill the circuit. So that might be the way to do it, is to use a varactor, right? A varactor, a variable capacitor, and you just dial it down, and it kills the circuit. See, I love doing videos. It helps me think out loud and get my brain juices working. That might be the way to throttle the circuit. Well, maybe not throttle. We may not be that lucky. You know, some of these circuits are so explosive, you get incremental jumps of humongous amounts, and you don't get to easily, at least readily, apparently, know how to throttle in a nice micro-tuning manner. You simply throttle it in big jumps, and you got to live with those jumps unless you can figure out how to fine-tune the thing. And I don't know, that's going to be a whole nother mess, is knowing how to fine-tune it, because up front I may just be able to turn this thing on and off, and at least that'll be something. Because if I use a times clock to change the varactor to cause the circuit to come on and off within a certain parameter duty cycle, I can fake fine-tuning or throttling the output of this circuit by how much percentage it's on versus how much percentage of each cycle time that it's off. That's pulse width modulation, basically. So there you go. Maybe that's how we regulate this thing.